All right, so today we're going to kind of piggyback off of what we discussed last class period with these electron pushing arrows, using them in this very specific context known as resonance. All right, so we can use these electron pushing arrows to talk about reaction mechanisms. That's what we covered last class period. We can use those same arrows to talk about resonance in molecules as well. All right, so what we're going to see is a slightly different use than what we were doing last class. You had talked about resonance a little bit in Chem 1A when we were talking about Lewis structures. All right, so when we say resonance, what do we mean here? All right, so it turns out that not all molecules can be accurately represented by a single structure. Okay, so most of our molecules, we can just put that one bond line structure down and we know exactly what we're talking about. There are other molecules where one structure alone will not do it. All right, so instead we need to represent these with multiple structures. All right, and when we do that, our true structure is actually a hybrid of those two structures together. Or rather, let's say, so we don't overuse the word structure, the true molecule is a hybrid of those structures. All right, so let's look at an example from Chem 1A. This molecule is ozone. All right, and actually before we go here, everybody take a second. We got a bunch of oxygens. Take a second and fill in lone pairs and formal charges for me. All right, we actually got one of each here in our structure. Oxygen with a negative formal charge, oxygen with a positive formal charge, oxygen with a zero formal charge. So this one structure here does not accurately represent an ozone molecule. An ozone molecule doesn't have one double bond and one single bond. Instead, we need to put another resonance structure down. We use these resonance arrows here, these two-headed arrows. This is specific to resonance structures, so this is a resonance arrow. All right, and my other resonance structure here will have those same three oxygens, but what we'll see is we've shuffled around our electrons. So now the double bond is on the other side, and the single bond has swapped places. All right, and it's really the two of these together that represent accurately the structure of that ozone molecule. In addition to using our little two-headed resonance arrow, we also put our resonance structures in these brackets to kind of remind us that this is actually packaged together as one molecule. All right, so we're going to call these our resonance brackets. Okay, and again, the whole shtick here is that our true ozone structure is a hybrid of both of these molecules, both of these structures. Our true ozone molecule is a hybrid of both of these structures. All right, sometimes you might, actually let's take a step back and figure out what the difference is. Spot the difference between what's going on here in these two molecules. All right. Importantly, we can see that our double bond is in a different place on each of them. What else is different? The charges, which is caused by lone pairs, right? So they're the lone pairs as well, okay? So for example, we got 3 lone pairs on this side, 3 lone pairs on this side, okay? And what people are tempted to do is think about these as these jumping back and forth. These electrons are kind of switching back and forth between these two positions, okay? And this is one of the hardest things to kind of wrap your head around, because that's almost what it looks like we've just drawn here, is that it's switching back and forth between the two. But really, it's the hybrid of both of these together that's the true form of this molecule, right? The weird thing about electrons is, yes, they are particles, but within a molecule, within those orbitals, they also can behave like waves. And so these electrons are spreading themselves out to both of these positions at the same time. So neither one of these structures is true at any point in time. It's both of them together that's the true form of our molecule. And sometimes you'll see that represented using these like dotted lines. Kind of like, look, the electrons are moving between these two positions. We really don't like this because it does not accurately represent our formal charges and how many electrons there are, et cetera, but it is kind of a nice little picture to have in your brain, this idea of these electrons spreading themselves out to those two positions, okay? So this idea of electrons spreading themselves out between multiple positions is what we call delocalization. All right, whenever you have resonance structures, you have the delocalization of electrons. This is electrons spreading themselves out across multiple positions. In a molecule. All right, most molecules, this doesn't happen. The electrons are localized in a bond or in a lone pair, but there are certain special molecules, and we'll learn how to spot patterns where these electrons can actually spread themselves out to multiple positions. And whenever that does occur, whenever we do have multiple resonance structures, it has this stabilizing effect on these molecules. Right? These electrons are negatively charged. The more that they can spread themselves out, the less concentrated that charge is, and so the more stable that molecule is. So anytime a molecule has multiple resonance structures, that's a hint at how stable that molecule is. All right? So we just want to note, okay, this delocalization has a stabilizing effect. Okay. As we discussed, molecules really don't like to have, or rather atoms don't really like to have formal charges. That's always a higher energy state to have a formal charge associated with it. One thing that can make a formal charge more palatable for a molecule is if it can spread it out across multiple resonance structures, right? So spread out those charges. Okay, so we can represent the electrons sort of moving between these various positions using our electron pushing arrows. All right, so let's just look at an example using this system that we set up with ozone, and then we're going to lay out some rules for drawing these electron pushing arrows, specifically in the context of our resonance structures here. All right, so electron pushing arrows in resonance. Okay, so we would have this pair of electrons coming down to form our new carbon-carbon double bond. This would be our bond formation arrow here. And then we can't break oxygen's octet in the middle. We can't just stop there, or it would have too many bonds. So at the same time, we're going to bump this pair of electrons up onto that oxygen atom. All right, that would be a bond breaking arrow. Okay. Or we could go the other way if we had instead started with the structure on the right. Again, kind of the same thing, but opposite. We'd have this pair of electrons coming down to form our new bond. And then we'd have this pair of electrons jumping up to form a lone pair. Okay. So all of our normal rules for electron pushing arrows apply for resonance, all right? But in order to be considered resonance, we're going to add two more rules on there, right? So these are in addition to what we talked about for our electron pushing arrows previously. In order to be resonance in particular, number one, you can only move lone pairs and pi bonds, not sigma bonds. Okay. This is not a true rule if we were talking about our reaction mechanisms, but again, specifically within the context of resonance, we got to follow this rule here. We can only move lone pairs and pi bonds. So first of all, let's take a step back. What the heck do I mean by a pi bond and a sigma bond? All right, let's just remind ourselves, this is terminology we threw around in previous semesters. Let's say we have a carbon-carbon sigma, well, that kind of gave it away. A carbon-carbon single bond. What type of bond is that? A sigma bond. All right, and then if we have a double bond, so for example, our carbon-carbon double bond, one of those is still a sigma bond, but the other one would be a pi bond. Okay? And we'll talk a little bit more about this when we talk about compounds that have these carbon-carbon double bonds, but it had to do with the geometry of those electron orbitals. In a sigma bond, it's exactly kind of how you would picture a covalent bond. The electron density that's being shared between two atoms is located directly between those two atoms. Pi bonds have this weird shape associated with them. The electron density isn't between the two atoms, but rather above and below, okay? And then lastly, if we have a carbon-carbon triple bond, or really any triple bond, what would we have here? 2 pi bonds and 1 sigma, right? So basically the first bond is always a sigma bond. Anyone after that would be considered a pi bond. All right, so just going back to our previous example, just convince yourself real quick that I only moved lone pairs and pi bonds. That's the only thing we're allowed to do for resonance structures. Again, that's not true for general reaction mechanisms, but it's true within the context of resonance. Okay, the other thing that we're not allowed to do, and this is kind of just true always, but important to keep in mind, is we can never break the octet rule. There is one exception. What exception is there? Whose atom do we sometimes break the octet rule for? Carbon, and specifically in forming those carbocations that have fewer than 8 electrons. Carbon will still never have more than 8 electrons, all right? So you don't want to overload its octet rule, all right? But we are going to put except those carbocations. All right, so just to kind of illustrate what we're going to call forbidden resonance moves. Okay. We can draw, there's actually nothing illegal about what I did with my arrow here. I could draw the product of this jump. I'd have that bonding pair of electrons becoming a lone pair. All right, since I stole it from that other carbon, it would have a positive charge or be a carbocation. But why is this not allowed in resonance? I broke a sigma bond, right? So that's not allowed in resonance here. So again, no breaking of sigma bonds. All right, likewise, in the previous example, we had a lone pair from oxygen come down to form a new double bond. So at first glance might look similar to what we did above, but what's the problem here? All right, everybody's organic chemistry brain needs to explode when they see a carbon with 5 bonds associated with it, right? That can just never happen. So again, can't break the octet rule. All right, this right here is, whoops. Not what I meant to do. This right here is super problematic. Cool. All right. So we talked about what's allowed in terms of our resonance, but how are we supposed to be able to tell whether a molecule has resonance or does not have resonance, whether it has these delocalized electrons or not? Okay. So for that, we're going to talk about spotting what are called resonance patterns. These are certain patterns that if we see within a molecule, we know that molecule has resonance structures. Okay? Actually, before we introduce these resonance patterns, there's a vocab word that I got to throw at y'all. All right? And that is allylic. All right? So, what does it mean to be the allylic position? This is the position in a molecule one removed from a double bond. Let's call it actually just a pi bond. We'll make it more general. All right. So in this molecule here, we're going to identify all the allylic positions. All right. The carbons about that double bond are not allylic. We call these vinylic. All right, so I'm not talking about the ones that are about the double bond. I'm talking about their next door neighbors. So these four positions, 1, 2, 3, and what's at my fourth allylic position? It's not explicitly represented, but implied in our bond line structures. My hydrogen, right? There's a hydrogen sticking up right here. This would be the fourth vinylic position. Allylic position. All of these are the allylic positions in this molecule. All right, that proximity of being next to that double bond is actually really important. And then this one over here is nothing. It's just too far away. We don't got a special name for that. All right, but if we're talking about the allylic position in a molecule, we're talking about one removed from that pi bond. So next door neighbors to that pi bond, not the ones about that pi bond, but one removed. All right, so again, in blue here are all my allylic positions. Cool. All right, we're going to throw that term around a lot, so we just want to make sure we got that vocab word down. All right, so our first resonance pattern that we want to be able to spot, a molecule that will always have resonance, is if we have an allylic carbocation. Whoop. All right, so let's just draw an example here of an allylic carbocation. Again, I'm going to need that carbon-carbon double bond. Oops. All right. And if I'm going to do the allylic position, let's call these A, B, C, and D. Where's that carbocation going to go if it's in the allylic position? C, right? Not about that double bond, but one removed. So in this case, right here. Okay, so our allylic carbocation, the important thing to remember here is that carbocations have incomplete octets. So they can accept electrons. All right. I'm going to put in the electron pushing arrow, and I want you all to try to follow that here. We're going to start out at this bond here, and that pair of electrons is going to jump to that positive charge. Okay. I will tell you that this is a bond breaking and formation arrow. So see if you can't draw me my other resonance structure here. All right, so what you want to kind of have in your mind's eye, what you want to be imagining, let me see if I can sort of draw this out here. I have my carbon-carbon pi bond here, right? If it's going to move over to that carbocation, it's going to flip around to the other side here, okay? So then my carbon that used to be, or that's on the end here on the very left, it used to have this complete octet, all 8 electrons. When I flip that double bond around, now all of a sudden I stole that pair of electrons from it, right? So in order to keep everything charge balanced, I'm basically going to swap positions of my pi bond and that positive charge. So my other resonance contributor, now my pi bond's located over here in the middle, and that carbocation is located on the end. All right, so maybe we can just note our pi bond and carbocation swap. All right. What else am I going to need to finish this off to be a true resonance structure? The brackets. All right, so let's be good and put our resonance in brackets here. Okay. Again, both of these structures are true at the same time. One of the things that we're going to see that's kind of interesting is that those electrons are kind of spread out here. If we look at our positive charge, though, on this structure, it's over here on carbon 3. On this one, it's on carbon 2. It kind of jumps over that on carbon 1, kind of jumps over that carbon 2 position, right? And so this would be important for this molecule and the reactions of this molecule. What we'd see is that carbon 1 and carbon 3 are really reactive, but not carbon 2 and carbon 4. Okay? So your resonance structures, again, are showing you where that charge is being stabilized across your molecule. All right, our next pattern is if we have a lone pair that's adjacent to a carbocation. Okay, again, our carbocation has an incomplete octet and can accept electrons. In this case, they're not going to be bonding electrons, they'll be those lone pair electrons. All right, so let's get an example here. All right, so if I was going to draw my resonance electron pushing arrows, I'd have a lone pair coming down to that carbocation. Is this a bond breaking or a bond formation arrow? Formation, right? I'm starting at my lone pair. One thing that I just want to point out that somebody asked last class that I thought was a really good question is like, how do I know that it isn't just this lone pair? Let me see if I can illustrate this. This lone pair that's jumping over to this atom here, okay? That is never the case. Pairs of electrons don't jump from one atom to the other, right? So it's always going to be associated with that oxygen. So instead, my new structure here has that bond formation pattern. That lone pair is becoming a bonding pair of electrons. It's not like the lone pair is skipping from one atom to the other. It's becoming a bonding pair. All right, because my oxygen now has 3 bonds and 1 lone pair, it's got that positive formal charge. And again, I'm going to put these brackets around it. All right, so actually what I would love is for everybody to go back to their notes when they were discussing electron pushing arrows. And we discussed these patterns that we expect to see. And let's just put that we will never see a lone pair jumping to an adjacent atom. All right, that's not something that's allowed to happen. Lone pair becoming a lone pair. Okay, you could kind of convince yourself by drawing out examples that you wouldn't be able to do this without violating something's octet. All right, but we're just going to note this is not allowed. Cool. So we got 2 of our resonance patterns here that we can spy. We got 2 more. One uses that same vocab word we introduced if we have an allylic lone pair. This is the case that we saw in ozone. You can convince yourselves that in that molecule that we started out with, we had this lone pair in that allylic position, one removed from this double bond. Okay, we'll put down another example here. All right. So my allylic lone pair, my lone pair here can move into the p orbital of this pi bond, but I'm actually not allowed to stop there. All right. What would happen if I stopped there? How do I know that that's wrong? Let's draw it out. Well, first of all, I'm messing everybody up because that's not an allylic lone pair. There we go. My bad. I was too far removed. Just making sure everybody was paying attention. All right, again, I can't stop just there. Let's see why. What's wrong with this structure? Carbon with 5 bonds. Everybody's organic chemistry brain explodes. So instead, we got to also move that pi bond pair of electrons onto that carbon atom. Forming a carbanion in this case, that negatively charged carbon. All right, you can notice that in this case we actually had to make 2 jumps. All of our other patterns are just 1 resonance arrow. This one actually required 2. We had 1 bond formation arrow and 1 bond breaking arrow. All right, and the last one, our last resonance pattern here is when we have a pi bond between atoms of differing electronegativity. All right, so let's take a second and review what the heck electronegativity means. Get a periodic table here. All right, don't worry about all that. We're not doing nuclear. That would be, yes, correct. The radioactivity. Okay, so electronegativity here. What the heck do I mean by electronegativity? It's a really important concept, especially in organic chemistry, because we're talking about covalently bound molecules. So first of all, who remembers there's one most electronegative element? The electronegativity champion on the periodic table is which element? Fluorine. All right. So what does it mean that fluorine is the most electronegative? So electronegativity is the ability of an atom to pull electron density in a covalent bond. All right, so what the heck do I mean by that? Okay, so first of all, when we say covalent bond, everybody says that that means sharing of electrons, right? And that sounds like this nice, neat agreement between those 2 atoms where they're like, yes, I will share my electrons with you. No, in reality, those 2 atoms are engaged in this epic tug of war over that same pair of electrons. That's what's keeping them bound together, is they're both pulling on that pair of electrons. And it turns out that some elements are just better at tug of war than other elements. Fluorine is the tug-of-war champion on the periodic table. When it's in a covalent bond with any other element, it's able to pull that electron density onto itself. So they're sharing that pair of electrons, but it's not an even sharing. Fluorine, or the more electronegative element, is pulling that pair of electron density onto itself. Okay? So the closer you are to fluorine, the more electronegative you are. All right, so that's kind of an easy way to spy electronegativity in comparison between atoms. Cool. So then if we go back to our resonance pattern here, we need to have not a single bond, but a pi bond between two atoms of differing electronegativity. Which one of these is the more electronegative element, oxygen or fluorine? Oh, oxygen or fluorine, hello. Yes, fluorine, okay, but that's not on here. Oxygen or carbon? Oxygen, right? Oxygen's right next door to fluorine. It's actually the second most electronegative element. So oxygen is able to pull that electron density in from that pi bond onto itself. All right, so everybody take a second and draw me what my other resonance structure would be here. All right, and it's always going to be the more electronegative element pulling the electron density onto itself. All right, so my oxygen took that pi bond and turned it into a lone pair, right? Pulled that electron density onto itself. What am I missing from my structure on the right? Charge, and which charge? Positive charge, right? Because over here my net charge is 0. Over here it better be 0 as well. So again, carbocations are kind of the hardest to spy here. But again, this carbon down here got that pi bond. It used to have a nice, happy, full octet. It got that pair of electrons ripped away from it, leaving us with a carbocation. Okay, so these are our 4 resonance patterns here. One more vocab word that I'm going to throw at you because I'm sick of not saying it because it drives me nuts, and we will come over this over and over and over again. This carbon-oxygen double bond has a fancy name in organic chemistry. This is what we call a carbonyl group. That carbon-oxygen double bond. Okay, so anytime you see a carbon-oxygen double bond in an atom, we would call that a carbonyl group or a carbonyl bond. Cool. All right, so I'm going to put down some examples here. Okay, we're going to practice spotting resonance patterns. Okay, so what I'm going to do is I'm going to draw some molecules. You're going to tell me whether or not they have one of those 4 resonance patterns. If they do, you want to identify what that pattern is and draw in that other resonance contributor. All right. All right, and feel free to check your work with your neighbor at your table. Make sure you're on the right track here. All right, so I'll tell you, each one of these falls into one of those 4 categories. Try to identify which category that is, and then from there you can draw me the other resonance structure that we have. All right, I'm gonna float around, so grab me if you have any questions. This is, and all these other ones we just needed 1 arrow. There was one of our resonance arrows. We actually needed 2 arrows. Cool. All right, let's go through these. So step one, figure out what category it belongs to. If you can spy these patterns, it's going to make your life a lot easier in drawing your various resonance structures. So this first one here, what was our pattern? We got that carbocation in the allylic position, right? So that was one of our categories, an allylic carbocation. Okay. In an allylic carbocation, that carbocation can accept pairs of electrons. It's got that incomplete octet. And so it's going to accept that pair of electrons from that pi bond. Remember, we said in this pattern, kind of what essentially happens is that pi bond and that positive charge end up swapping places. All right, so I draw my new hexagon. Now my double bond's up here, and my carbocation's down here. All right, what about this next one here? Did anybody get what pattern we had? The pi bond between atoms of differing electronegativity, yep. Just going to say pi bond, different electronegativity. Okay, so that carbon-nitrogen, it's actually 2 pi bonds. Okay, but that more electronegative element can pull that electron density from that pi bond onto itself. Now my carbon only has 3 bonds, meaning it has that positive charge. And my nitrogen now has 2 lone pairs, meaning it has a negative formal charge. All right, our next one here, what was our resonance category? Lone pair adjacent to a carbocation. Again, that carbocation, as we've seen, really good at accepting pairs of electrons, but here it will be a lone pair that comes down. Again, that lone pair is not going to jump from the nitrogen just onto the carbon. It's going to swing down and form a new bond. So now I'll have a double bond between carbon and nitrogen. And what am I missing here? The formal charge on that nitrogen with its 4 bonds needs to be positive. All right. Now this last one's a little tricky because most of our resonance patterns we only had to draw 1 electron pushing arrow for, but there was that one instance where we had to draw 2. And we had that fancy term. This one is an allylic lone pair. All right, so I want everybody to take a minute. Based on what we discussed with our previous example of an allylic lone pair, put in your electron pushing arrows and draw me that resonance structure that's missing here. All right, so in our allylic lone pair, we actually make two jumps. One, that lone pair comes down into that p orbital of our pi bond, but we can't break carbon's octet, or rather we can't go exceed carbon's octet, so that pushes that pi bond pair of electrons into a lone pair. Okay. One thing I want to stress here is this arrow up top here. Remember, the head of your arrow has to point at an atom, and this is something that you will see incorrectly done, even in some textbooks, is something like this. Importantly, electrons do not accept other electrons, right? In fact, electrons don't really like other electrons because they're both negatively charged. It's the atom that accepts that pair of electrons, all right? You will see it incorrectly in some textbooks, but again, they're wrong, and we like to do things the right way here at Fresno City. Okay, so again, our rule of always having the head of an arrow at an atom is something important to keep in mind. Okay. All right, now let's talk about, we drew all these resonance structures. We know how to spy whether there's resonance structures. Let's talk about the stability of resonance structures. All right, so not all of your resonance structures are necessarily equally stable. All right, your true molecule looks the most like the most stable of those resonance structures. All right, but importantly, even if you can draw a resonance structure that's less stable, it is still very important to the chemistry of those molecules. All right, so even those unstable structures are important. All right, just because you're unstable does not mean that you don't matter. Right? Good life advice as well. Okay? So, for example, if we go up here, I think this one is a good example. If we just take a look at this, one of these resonance structures is definitely more stable than the other one. What do we think? The one on the left or the one on the right? The one on the left, right? The one on the right has a bunch of formal charge on these two atoms. It turns out, though, this is still very important to the chemistry of this molecule. This carbon in the middle here does indeed have a lack of electron density, has this relative positive charge associated with it. So even though this is what our true molecule looks more like, we still want to consider both of these resonance structures when we think about the chemistry of these molecules. Okay? So important things to consider when we're talking about the stability of these resonance structures. The most important thing is that your most stable resonance structure is the one where everybody has a complete octet. How did I say this? All right. So if we take a look at one of these examples that we laid out kind of at the very beginning, let me just go up and copy. This one here. Which one of these is the more stable of the two resonance structures? Let's take a poll. Who thinks it's the one on the left? Who thinks it's the one on the right? All right, so the one on the left is indeed less stable. This one is more stable. And why is that? Because remember, carbocations have incomplete octets. So the one on the left, everybody's got a complete octet. Oxygen's got a complete octet, even though it's got its formal charge of +1, it's got a complete octet, and carbon's got a complete octet, right? So again, your most stable structure is the one that has the most complete octets. All right, the second thing to consider, the most stable resonance structure has the fewest formal charges. Okay, so again, our example of this hydrogen cyanide here. As you guys kind of intuitively said, the one that's going to be more stable is the one on the left because it's got the fewest formal charges. All right, again, that doesn't mean that the one on the right isn't important, but again, our true molecule looks the most like the one on the left. All right, and the last thing to consider is if we have to have a formal charge, we want the negative charge to be on the most electronegative. And if we have to have a positive formal charge, we want it on the least electronegative. All right. So going up again back to one of these previous examples that we did. Okay, you can just go back up in your notes to where we talked about our allylic lone pairs. Which one of these would be the more stable of the two resonance structures? The one on the left or the one on the right? All right, so importantly, everybody's got a complete octet, right? So in terms of rule 1, it's a wash. But if we go down to, they both have the same amount of formal charge. So in terms of rule 2, it's a wash. We go down to rule 3 though, if we have to have this negative formal charge, we want it to be on the most electronegative element, which is in this case oxygen. So that's why the one on the left is going to be the more stable structure. Okay. Now, in some cases, as in this first example of our allylic carbocation, these are a wash in all three of those rules, right? These are tied. So in this case, they would be equally stable. But that's not always the case. Okay? All right, so then the last thing we're going to do is kind of tie this all together here. We're going to try to look at, we're going to sort of complicate our spotting of resonance patterns. We're going to look at structures that have more than two resonance structures. All right, so in these examples here, I want you to find there are actually 3 resonance structures that you can draw for these two molecules. All right, and one sort of tip I'm going to give you for when we're trying to find all of our resonance structures is you don't want to try to combine multiple jumps all in one shot. All right, so draw your single resonance steps to get all your contributors, all your structures. So both of these here actually have 3 resonance structures that you can draw for each of them. All right, so what you want to do is spy what pattern you have. Go ahead and make that jump to find your new resonance structure, and then take a look at that new resonance structure and see what pattern it has. All right, so in this first one, we had that allylic carbocation pattern. So we draw that, and when we take a look at our new resonance structure, that also has an allylic carbocation. So we can make that jump one more time. Okay, and again, why this is important is that this is important for the chemistry of this molecule. I'll just give you a little bit of a preview. Carbocations will react with negatively charged ions like chloride ions, for example. And it turns out that your chloride ion would react with all three of these positions. And notice it's kind of that every other carbon gets that positive charge. So that positive charge isn't spread out to all 5 carbons. It kind of jumps to every other carbon according to our resonance structures here. And that's what we see when we do the chemistry of these molecules. All right. So again, that's why we like to look at all of our resonance structures for a particular molecule. For this last one here, that first resonance pattern that we see is that pi bond between atoms of different electronegativity. So we're going to make that first jump with our electron pushing arrows, pulling that electron density onto that more electronegative oxygen. If I look at my next resonance structure, it has now a different type of resonance pattern. This is, again, an allylic carbocation. So in order to get all of my resonance contributors here, I got to consider both of those resonance patterns. Oops. Where now my double bond and my positive charge have traded positions here. All right, so all 3 of these together would be the correct or true structure of this molecule. Cool. All right. So next week we're going to be talking about acids and bases. We're going to both be using our electron pushing arrows to demonstrate the mechanisms for these reactions. We actually already showed some examples of that last class. We'll also talk about why resonance, and particularly the stabilization effect that resonance has, is important when we're considering how acidic or basic a molecule is. Cool. We ran over a little bit, so let's say that we're going to meet for lab at 35 after.